Hi everyone, my name is Jin Su. Currently, I'm studying Master of Business Analytics in University of Minnesota. And this paper is a joint work with my colleague in former company, Cathay Financial Holdings. In this video, I will talk about how we applied several mechanisms to improve BERT architecture. In recent years, unsupervised pre-trained models have dominated the field of natural language processing. And the construction of a framework for such models involves two steps, pre-training and fine-tuning. During pre-training, an encoder neural network model is trained using large-scale unlabeled data to learn word embeddings, and parameters are then fine-tuned with labeled data related to downstream tasks. Among these pre-training models, several famous methods such as Elmo, GPT, and BERT have attracted considerable attention with high accuracy in NLP tasks. As you may know, since Elmo uses the architectures of sequence-to-sequence, it falls short of GPT and BERT, which uses transformer instead. In this paper, we focus on BERT, which is the leading method that applies the architecture of the transformer encoder and outperforms other models on the Glue leaderboard. Its performance suggests that self-attention is effective in extracting the meanings of sentence embeddings. Okay, so let's dive deep into BERT. And actually, we could understand BERT as long as knowing transformer. And I guess you have known BERT already, so I'll give a quick summary about BERT. BERT's architecture is a multi-layer bidirectional transformer encoder, and it denotes the number of 12 layers and 8 multi-heads. In each encoder, BERT adopts multi-head rather than single-head attention, which benefits from linearly projects the queries, keys, and values multiple times with different projections. Also, each of these metrics is randomly initialized, so this allows the model to learn from different subspaces. For example, in the example above, Z1 contains a little bit of latent embedding from different subspace. As long as we have multiple head vectors, concatenating them together will be a meaningful vectors. So far, we know how BERT works. Although BERT's performance suggests that self-attention is highly effective in extracting the meanings of sentence embeddings, there exists some further improvement. Two questions arose about BERT architecture. First, although BERT model presented several options for its use, the layer selection approaches in all layers was still unclear. For instance, when inputting a sentence inside the model, the output data of different layers encode a wide variety of information, and some might be good, some might be bad. Therefore, layer selection is a question in BERT. Second, the self-attention mechanism enables a word to analyze other words in an input sequence. This process can lead to more accurate encoding and to capture global dependencies. On the other hand, from a linguistic intuition, when a word is aligned to another word, we expect these aligned words to capture the phrasal patterns that contain useful local context information. While the self-attention focuses on global dependencies, it doesn't focus much on this local dependency. Our contributions in this study is to improve contextualized word embeddings through two methods. That is squeeze and excitation alongside Gaussian blurring. It is worth mentioning that we didn't change the original method of the pre-training stage in the BERT model. We only make a change in the fine-tuning process. Okay, so let's look at our first method, squeeze and excitation. So by investigating relationships between layers, We observed that squeeze and excitation is the key for focusing on information between layer weights. This method enables networks to construct informative features by fusing local receptive field at each layer. To be more specific, it enables the network to perform feature calibration by selectively emphasizing informative features and suppressing redundant ones. Another point is that BERT focuses the global dependencies without regard to their distances. We argue that self-attention can be further improved by taking into account the local context by using Gaussian blurring. So take the example shown above. If bush is aligned to held with high probability, we expect the self-attention model to pay more attention to the neighboring words they talk. Consequently, the model can be guided to capture the phrase held a talk. Our Gaussian blurring method focuses on learning local contexts while maintaining long-range dependencies. To capture the local dependency related to each word, we use a predefined fixed window size k to create a Gaussian blurring vector. Then, doing convolution helps a word to focus on not only its own importance, but also its relationships with neighboring words. Several Gaussian blurring strategies are feasible for applying convolutional operations to outputs. For instance, we tried Gaussian blurring on attention outputs and on values output. We even did it with a two-dimensional Gaussian matrix, but the effect wasn't that good as we think. Eventually, we only tried Gaussian blurrings on attention outputs and value outputs. However, we still didn't have a conclusion which method is better. It all depends on cases. Other than evaluating our models using glue datasets, we want to make sure that our models they really learn rather than simply adopting shallow heuristics. Therefore, we used the Hans dataset described in the paper of Right for the Wrong Reasons. This paper investigated whether neural network architectures are prone to achieve success by adopting shallow heuristics rather than learning the underlying generalizations. They proposed that if the model uses the heuristic learned in 1, it incorrectly predicts entailments for 2. This is the case of lexical overlap, which is mentioned in the paper. The lexical overlap disregards the order of the words in the sentence and considers only their identity, that is, lawyer and doctors. The findings in the paper are that BERT performed well on glue tasks, but performed poorly on the Hans dataset, suggesting that the BERT models employs the shallow heuristics. Therefore, other than glue datasets, our experiments also used Hans datasets to diagnose some fallible structural heuristics presented in the paper. Before experiment, I want to talk about some reviews in our papers. Some reviews suggested us to compare our models with other facial models like AxelNet, MTDNN, Roberta, or even GPT-2. Well, the truth is that we released our model in summer 2019, and by that time, these models were still not being published. So we didn't incorporate those work in our paper. Well, I believe the work to compare with other models could be done in the future. But in this paper, we just focused on our architecture improvement via BERT. Okay, now let's get back to the experiment. In most of the glue tasks, our proposed method outperformed the original BERT-based model. For example, in the RTE and AX datasets, SesameBERT yielded improvements of 1.2% and nearly 2%, respectively. Also, we conducted experiments on these datasets to test the effects of Gaussian blurring alongside BERT on the value layer and context layer. We performed 3 ablation studies. First, we examined the performance of our method without blurring, and we observed that squeeze and excitation help in the higher layer. Overall, this trend suggested that higher layers benefit more than lower layers from squeeze and excitation. Second, we analyzed the effect of Gaussian blurring on the context layer. The results revealed that the method without blurring also achieved higher accuracy. We assume that capturing short-range dependencies among neighboring words in lower layers is an effective strategy, since lower layers learn better than higher layers, so it could capture more on blurry effects. Even if self-attention models capture long-range dependencies in higher layers, modeling localness remains a helpful metric. Finally, we observed the direct effects of SesameBERT on various layers. Although our proposed architecture performed poorly in lower layers, it outperformed the other methods, BLURBERT and SeBERT, in higher layers. So these findings indicated that in higher layers, using our method helps self-attention models to capture more information in all layers and the neighboring words. Now, regarding to Hsiang dataset, we trained both BERT and SesameBERT on the NNLI datasets, which is on glue datasets, to evaluate their classification accuracy. And BERT is a little bit higher than that of SesameBERT. However, in the Hsiang dataset, we explore the effects of 2 models on each type of heuristics. On the left figure, for which the label was entailment, we can see that both models perform well, and it represents the models adopt the shallow heuristics. Next, we evaluated the heuristic labeled as non-entailment on the right figure, which is the figure we want to focus on. We can see that BERT performed poorly for all 3 cases, meaning that BERT assigned correct labels based on heuristics instead of applying the correct rules of inference. By contrast, our proposed method performed almost 3 times as well as BERT in the case of lexical over depth. And this indicated that the model did learn from the latent information that it intended to capture, which verified the idea that Gaussian blurring can prevent models from easily adopting heuristics. In sum, we propose 2 approaches to improve the performance of self-attention network. Specifically, we aim to extract information from all layers through squeeze and excitation. Additionally, we adopted Gaussian blurring to help capture local context. Of course, the cost is that our method could have a high computation, so maybe it's an issue that needs to be solved in the future. Even so, we believe these 2 methods could be further integrated with other state-of-the-art models and make improvement. On top of this work, I want to thank my supervisor, Zhenshe Wu, who faithfully supported us to make innovations all the way. Also, I want to thank Cathay Financial Holdings. By the time we finished the paper, we were data scientists working there, and the company provided us the great computation environment with multiple GPUs. If you have further questions related to this paper, feel free to contact me. Thank you.